Our next speaker is Julien Rosen, and he will talk about p-adic periods of number fields.
Right, thank you for the introduction. So I want to start with a, minor technical difficulty here. There we go. Okay. So I want to start with a sort of a broad question. So take your favorite real number, and I'm thinking of something arithmetically interesting. So I listed here some examples of the kind of numbers I'm thinking of. So pi and e, of course, everybody knows that Euler's constant gamma, golden ratio is interesting. This g here is Catalan's constant that shows up. There are also like special values of zeta function, gamma function, this kind of thing, and there are many others. So this is just sort of a sample of the kind of numbers I'm thinking about. And the question I want to ask is, can you find an analog of your favorite number inside the p-adic numbers in QP? Or possibly analogs, right? Some of these numbers have more than one analog. So in particular, for these special functions, for the zeta and the gamma, there are a few different ways you can try to generalize these functions to the p-adics. You really get a bunch of different zeta functions corresponding to different residue classes mod p minus 1. The gamma function, there's this Morita p-adic gamma function. Jack Diamond has this p-adic analog of the logarithmic derivative of gamma. It's actually a different function defined in a different domain than Morita's function. So this question is, I'm not planning to give a sort of a total answer to this problem, right? The situation is that there are really a lot of different perspectives on finding p-adic analogs of real constants. And I'm just going to talk about one perspective on this today. So let me describe the class of number that I'm thinking about. These are numbers given by integration, right? So integration is one way to sort of get transcendental real numbers. Another operation you could think about is infinite summation, and that's also an interesting problem you could ask. I'm going to be focused on integrals for today. So I have just a bunch of examples of sort of arithmetically interesting integrals, right? Of course, you can get pi. There are many different integrals that give pi. Logarithms you can get this way. This e of k, this is the complete elliptic integral of the second kind. I wanted to write down. Special values of the zeta function, actually zeta of n, for every n greater than or equal to 2. There's sort of a similar integral expression for this. And this is, rather than just a single integral, a triple integral over this set, I guess this a simplex sitting inside R3. Then also this ratio of gamma values, right? This is the beta function is given by this integral. Okay, so these are sort of the kind of numbers I'm thinking about, and these are examples of periods. So let me give a definition here. Okay, so an effective period is a complex number. So I'm not just going to be restricting to real numbers. I'm going to allow complex numbers also. Doesn't make much of a difference. So an effective period is basically a complex number that can be written as the integral of an algebraic function over a semi-algebraic set, such that the function and the set are defined over Q. So a semi-algebraic set is just a subset of Rn defined by finitely many inequalities of polynomials. And the defined over Q, I just mean the defining polynomials should have rational coefficients. Right, so some of these functions are actually rational functions, some of them are algebraic functions. In these cases, I guess I should restrict to actually get a period. I should restrict to R being maybe in Q or maybe in Q bar. To actually have this be an semi-algebraic set defined over Q, the interval from 1 to R. Here K, maybe I want to restrict to K in Q bar or something. Down here in this example, so that x to the a and 1 minus x to the b are actually algebraic functions, I'm probably interested just in the case where a and b are rational numbers. Of course, these quantities make sense, whether or not a and b are rational, k is rational. But to get a period, we really should make this restriction. Okay, and then I just wanted to mention that there are some numbers, some familiar real numbers are conjectured at least not to be periods. So E is thought not to be period, Euler's constant gamma, and something like 1 over the log of 2 is expected not to be a period. I should say conjectured because actually there aren't, I think it's true that there are no examples of sort of naturally occurring real numbers that are interesting that people know how to prove are not periods. This is just sort of a hopeless problem. The collection of periods I can mention actually includes all algebraic numbers. So proving a number is not a period is strictly harder than proving that that number is transcendental. And already that's a hard problem. We're like, we don't even know if Euler's constant is rational or not, let alone transcendental, let alone not a period. But so one can at least make conjectures sometimes about certain numbers not being periods. All right. Let me just mention also this term effective period. There is a more general notion of not effective period, which should just be an integer power of 2 pi I times an effective period. I'm basically only going to be worried about the effective periods, but there is this slightly more general notion. Okay, so what can we do? Why are periods interesting? Well, so the reason is basically that there's this connection coming. You can think of periods as real numbers sort of coming from algebraic geometry in some sense, right? So if we're integrating an algebraic function, you really want to think of an algebraic function as being a function defined on an algebraic variety. So to set up here, I'm going to think of x is just being some algebraic variety defined over q. I could also make this definition with q bar, and ultimately we would get the same class of numbers. There's sort of a meta theorem that says that all definitions of period are equivalent. So there's a lot of flexibility in this definition for little things you can change where you ultimately get the same class of numbers. Okay, so I'm going to take x to be defined over q, and then y is going to be a subvariety. And then I'm going to consider these two relative cohomology classes. The Betti cohomology, right? So this is just the singular, the topological cohomology of the complex points. And then we also have this more algebraic theory, this algebraic de Rham cohomology. And you think of a class in the algebraic de Rham cohomology as being represented by an algebraic differential form. Okay, so you think of a Betti cohomology class as being a function on cycles, a q-valued function on cycles, and a de Rham cohomology class is represented by a differential form. That isn't quite precise, but that's sort of the picture to have in mind. So these are finite dimensional vector spaces, and there's a comparison isomorphism between them when you extend scalars to C. Right, so let me just say sort of briefly how you should think about this isomorphism. Well, you should think of a de Rham cohomology class in Hn as being represented by an n form. Omega is a differential form, differential n form defined over Q. This isn't quite accurate. If x is affine, every cohomology class is actually represented by an honest form. Not true if x is not affine. And this then maps to, well, an element of the Betti cohomology tensored with C, you should think of as a complex valued function on cycles. So this should be the function that takes a cycle to the integral of the form over that cycle. So this comparison isomorphism really does sort of record the idea of integrating algebraic differential forms over algebraic cycles. Okay, and I said matrix coefficients of this map. So this is a finite dimensional vector space. This is a finite dimensional vector space. If you pick a basis, you can write this comparison map as a matrix with entries in C, in the complex numbers. And the matrix entries really are integrals of algebraic differential forms over algebraic cycles. So the matrix entries are sort of a fancy way to talk about periods in the previous sense. Integrals of algebraic things over algebraically defined sets. Yeah, so I guess this is one problem with my system is this writing is going to go away when I put up the next slide. Well, yeah, I guess we'll live with this. So we can really think of comp as being sort of represented, like there's the matrix of comp sort of lives in some GL, I guess GLK, where K is the dimension. These vector spaces always have the same dimension. So we can think of the comparison map as being a matrix. Of course, the matrix itself depends on a choice of basis, but the Q span, for example, of the matrix entries is independent of a choice of basis. So you really do get a well-defined sort of space of periods coming from this setting. And then I really wanted to say that ultimately we should think of this Hn as being a motive. And you can actually do a similar construction for any motive, not just sort of one coming from a variety. If you don't know what motives are, just think of it as being sort of a piece of the cohomology of a variety. Okay, and then the Grothendieck period conjecture actually says that given a number that is a period, well, one can write down sort of a motive that has that number as a period, but the motive, the sort of the minimal motive where that period occurs is well defined up to isomorphism. This is a consequence of this conjecture. So for any given period, there is sort of a unique minimal motive that it comes from. And let me mention also that this definition, if one looks at matrix coefficients for this comparison isomorphism, for x and y varying over all varieties, one really does get the same class of numbers that I defined on the previous slide. Okay, so why talk about periods this way? The point is there's a nice p-adic generalization to this story. So we're going to replace this, I guess on the previous slide, sorry, I had this tensored with C. I mean, there is also a map if you don't tensor with C on the left. But yeah, the way I wrote it on the previous slide, sorry, had a tensor C. So we're going to replace this map. So this is sort of a transcendental comparison isomorphism, right? It comes from integration. There is a sort of a transcendental p-adic operation on cohomology. And this is the crystalline Frobenius map. Crystalline, or I guess rigid cohomology, gives you something like this Monsky-Washington cohomology in sort of different settings. People oftentimes use the word crystalline as sort of the catch-all term for this p-adic isomorphism. So it gives you an endomorphism of the de Rham cohomology tensored up with QP. Okay, and so the definition I want to make is that a space of p-adic periods of a pair is just the Q span of the matrix coefficients for this crystalline Frobenius. Okay, and more generally, you can do this construction with a motive also. So let me just sort of write out this recipe. So given a complex number that's a period, well, assuming the Grothendieck period conjecture, you get sort of a minimal motive M with that as a period. One doesn't have to assume the conjecture to write down what that motive is. Sort of knowing that it's unique is what the conjecture says, but in practice, you can just oftentimes write down what this motive is. And then associated with this motive is a space of p-adic periods. Okay, so this is a little bit strange in that I'm not exactly answering the motivating question. This recipe associates with any complex period a finite dimensional vector space of p-adic periods. And in general, there's no way to say, oh, this one particular p-adic number is the p-adic analog of your period. But there is sort of a finite dimensional space that's the space of p-adic periods associated with a complex period. Let me say also that there is some information is lost looking at p-adic periods. The space of p-adic periods of a pair xy is in general a smaller dimension than the space of complex periods. If one assumes the Grothendieck period conjecture, then this would follow from the Grothendieck period conjecture that the space of p-adic periods is bounded above by the dimension of the space of complex periods. Let me mention also, right, since there isn't this sort of actual correspondence, I'm not telling you that there's one particular p-adic period that corresponds to a real period. So there isn't really a homomorphism between the space of complex periods and the space of p-adic periods. But something I'm going to say is kind of BS. Forgive me. The thing that would want to be the homomorphism, even though this homomorphism doesn't exist, has a kernel. Is some way of saying sort of the information is lost on the p-adic side. I'm not going to try to make that precise right at the moment. Okay, let's look at an example where we can actually write this down. So let's take the log 2, right? Integral from 0 to 1 of dx over x. That's sort of the simplest integral. Dx over x is a one form, has a singularity at the origin. So I'm thinking of it as a one form on the punctured line. And then since we're integrating from 1 to 2, I'm thinking of this interval from 1 to 2 as being a cohomology class whose boundary is contained in the set 1, 2. So I'm really thinking of the region of integration well, I guess as a homology class, a relative homology class for A1 function at the origin relative to the subset 1, 2. Okay, so this is a two-dimensional space, a basis for H1. Well, it's dual to these two paths, the path from 1 to 2 and a loop around 0. And a basis for the de Rham cohomology is given by these two forms, dz and dz over z. Okay, and we can write down the comparison map. It's just a matter of sort of unwinding the definition, right? You integrate these forms over these two paths, and you get this matrix: 1, 2 pi I log 2, and then there's a 0 down here. So this is the comparison matrix for this cohomology group, the complex comparison matrix. You can also work out, though, what this crystalline Frobenius does on this cohomology. And I'm just going to tell you that the matrix looks like this. So you get a 1, you get a p down here instead of a 2 pi I. This is one of the sort of strange things. P is sort of, in this setting, the kind of the p-adic analog of 2 pi I, right? This integer p. So, right, okay, so it's sort of maybe a loose analogy, but then you do see this, this p-adic logarithm showing up in this matrix. So this process does sort of tell you, right? You sort of feed in log of 2, and it sort of tells you, oh, here's this number, p-adic logarithm of 2. That's sort of a p-adic version of that. Okay, you shouldn't take these two matrices too seriously, because I chose a basis for each one of these spaces, and if I chose a different basis, the matrices maybe don't line up so well, right? This is sort of only telling you that the span of these numbers, I guess this is, the Q span of 1 and the p-adic logarithm of 2 inside QP is sort of the space of periods corresponding to log 2. Okay, in this particular case, you would really want to say, oh, p-adic logarithm of 2 is the analog of log of 2. But the recipe I'm talking about doesn't sort of pinpoint that particular element. Okay. So I just wanted to mention a couple of other examples. So there are these multiple zeta values. These are real numbers generalizing values of the Riemann zeta function at positive integers. Deligne has a construction of p-adic multiple zeta values coming from looking at the coefficients for the crystalline Frobenius acting on, in this case, it's a motive, the motivic fundamental group of the line punctured at 3 points. Okay, and then sort of another sort of instance of this notion of p-adic period. August has a p-adic analog of the Chauer-Selberg formula, also coming from sort of thinking about matrix coefficients for the Frobenius acting on the motive associated with an elliptic curve. Okay, so maybe that's all I will say about these examples. Let me tell you sort of briefly what happens in dimension 0. So one of the reasons that people like to think about periods in this way is that there's sort of a conjectural version of Galois theory for periods, right? Periods are oftentimes transcendental numbers. There's still a sort of a version of Galois theory that they expect to hold for this. And the idea is that in dimension 0, if you restrict to dimension 0 varieties, you should really just recover the classical Galois theory. And so going from dimension 0 to positive dimension is this generalization. So let me just tell you what this looks like in dimension 0. So a 0-dimensional variety looks like the spectrum of a number field. This is 0-dimensional variety over Q. The 0th de Rham cohomology, this is the only non-trivial de Rham cohomology group, is just L itself. 0 forms are just functions on spec L. That's just L. All right, and the 0th Betti cohomology looks like this. It's rational functions, Q-valued functions is what I mean, on the set of complex embeddings of L. Okay, and you can write down this comparison map. It looks like this, and you sort through the definition, and it really just comes out that the complex periods of spec L are spanned by the complex images of L under all the embeddings. Okay, so one really just does get sort of a space of algebraic complex numbers as periods of a 0-dimensional variety. Okay, and so I wanted to just say quickly what happens with the p-adic periods associated with a number field. So L tensored with QP, maybe you know this, right? For any rational prime P, looks like a product of the completions of L at the different places of L lying over P. Okay, if P is unramified in L, then each one of these local extensions, LP over QP, comes with a distinguished local Frobenius. And the crystalline Frobenius, right? This is supposed to go from H0 de Rham of X tensored with QP, which is just L tensored QP to itself. It is just the product of the local Frobenius maps. So in this case, it's something really concrete, right? There's something you can write down. And so I'm yeah, let me just tell you what comes out to be the case with these periods. So the theorem is maybe not so surprising. It's that if you take an alpha and QP, then two things are equivalent. If alpha is algebraic over Q and Q adjoint alpha is unramified at P, this happens if and only if you can find a finite extension unramified at P, such that alpha occurs as a p-adic period of that extension. Okay, so the statement is maybe not so surprising. The proof actually is maybe more difficult than it seems. You can't just take L to be Q adjoint alpha. In general, given an alpha, you need to take the L to be a much larger extension. One way to see this is for abelian extensions. The p-adic Frobenius, you don't need to extend scalars to QP to get it. It's already defined. There's already a well-defined automorphism of the field itself. That is the p-adic Frobenius. And so all of the p-adic periods are rational if you started with an abelian extension. So if you take something as simple as a p-adic quadratic number, you already have to look for a non-abelian extension in order to find that number as a p-adic period. Okay, so it is 3 o'clock, so I will stop here and yeah, ask for questions.